Hello and welcome to Zetec's webinar on improving flaw detection in aerospace with advanced technologies. My name is Wayne Waxman. I'm the Director of Marketing at Zetec. I'd like to thank everyone for joining us today. I do have a couple of logistical items before we get started. Everyone is in listen-only mode, and we are recording today's session so you can review and listen to it or share with your colleagues in your organization. Everyone who registered for this webinar will receive an email later on with a link to the recording. Finally, there will be a Q&A session at the end of this webinar. You don't need to wait until the end of the webinar to send in a question though. At any time, just type your inquiry in the questions section on your GoToWebinar panel. Before we begin the webinar, I'd like to give a quick overview of Zetec. Zetec is a global NDT leader. For 50 years, we've advanced the science and standards in both ultrasonic and eddy current technologies, setting new heights in inspection performance, productivity, and predictability. Zetec's proven expertise and complete product portfolio serve the inspection needs of our customers worldwide in transportation, power generation, manufacturing, oil and gas, and more. Zetec is a subsidiary of Roper Technologies. Let's get to today's session, which will be presented by Jesse Herron. Jesse is currently a product manager for Zetec. Previously, he was a software developer in the avionics industry, and he's been with Zetec in various engineering and product management roles over the past 10 years. With that, let's start today's webinar.
Thanks, Wayne. Hello, everyone, and thank you for joining the webinar. My name is Jesse Herron, and I'm the product manager at Zetec for all of the eddy current systems. I'll be covering both ultrasonic and eddy current advanced testing methods for improving flaw detection in aerospace. And many of these techniques will also apply to other applications for those of you who do NDT in other industries. So for this webinar, we're going to be covering the following agenda. Ultrasonic testing, the advantages of phased array UT, and Zetec's TOPAZ product family, and TOPAZ phased array UT applications, eddy current array testing, scan speed, signal to noise ratio, and sample rate with a demo to follow, friction stir welds also with a demo, and then multi-layer bolt holes with a demo. And we'll cover the MIZ-21C product family. So first we're going to cover ultrasonic testing from conventional UT to phased array UT. Just to give a brief intro into ultrasonic NDT, ultrasonic testing, or UT, is a practical and versatile non-destructive testing method that allows for full volumetric examination for components. A high-frequency sound wave from a transducer is induced into the material, and then anywhere where there are anomalies in the material, it creates echoes that are sensed for evaluation by specialized ultrasound instrumentation. It requires continuous material coupling for the sound to transmit and receive, and UT is used to detect subsurface flaws, corrosion, delamination, and many more applications. Although conventional UT is still common in the aerospace industry, the use of phased array UT is growing due to its many advantages. So the key difference between conventional and phased array UT is the transducer. And conventional UT uses single or paired element transducers, one for transmitting and one for receiving, so that to generate the ultrasonic waves. The acoustic beam is depicted in the image on the right and is divided into two parts. So there's a near field and a far field. And in the near field, near the transducer surface, sound pressure gradients create variation in the acoustic field energy pattern. And at the end of the near field, the sound pressure drops and the acoustic field becomes more uniform, with one point containing the maximum acoustic energy, and that's called the focal point that's shown there. Because the far field is more suited for flaw detection and sizing. A probe is typically selected to inspect material located in the far field. So to obtain an angled beam, a conventional UT transducer is paired with a wedge. The crystal inside the transducer generates a wavefront, and since the transducer is now at an angle relative to the material being tested, waves will hit the wedge slash material interface at different times. As explained by Huygens principle, each part of the incoming wavefront acts like a single point, like a spherical wave generator. When these points reach the interface, they will start to generate new spherical waves traveling at different velocity because of the change in the medium. The delays introduced by the wedge, coupled with the ratio between the velocities, as Snell's law, determine the new direction of the overall wavefront. In the case of angled beam transducers, most wedges are designed such that the near field is contained within the wedge. So unlike conventional UT, which contains only a single or paired elements, a phased array transducer contains from 16 to as many as 256 individual elements. If each element was pulsed at the same time, the resulting phased array beam would look the same as conventional UT beam. However, with phased array technology, individual activation of each element is possible through using the software. So control of the activation of individual probe elements is the key benefit for phased array over conventional UT. It allows the user to quickly and easily optimize the beam characteristics, aperture size, steering angle, and focus for a specific application. In contrast, the conventional UT requires the user to physically change probes, wedges, or lenses. And here is an example of phased array beam forming with creating a wavefront. And the applied delays, which is with focal law, will serve as a wedge to create an angled beam, the crystal curvature for focusing, or both. So another benefit of phased array technology is the ability to select the area of the probe that will produce the beam or move the aperture along the probe. So in contrast, conventional UT, the user would have to move the probe back and forth toward a weld, for example. Also in phased array UT, it allows the user to select specific position for the generation of the ultrasonic beam and optimize the beam exit point for an inspection. So here's showing the aperture position movement. So usually the selection of aperture position is more used for electronic scanning, also known as a linear scan. It's basically a way to replace hand motion with a comb of ultrasonic beams. So here you can see the animation using the aperture position to simulate the hand scanning. So the basic idea behind beam steering is capability is to partially replace wedges in order to obtain angle beams, either linear wave or shear wave. These are limitations to the steering capability that come with the design of each probe. But let's say for now that it's related to the capacity of sending sound in a direction with a natural beam opening for each individual element. So in summary, phased array UT delivers a number of important advantages over conventional UT. Better control of the beam characteristics, translates to better flaw detection and visualization, and more efficient and flexible inspection solution. And since the inspection can occur at multiple angles in a single scan, phased array inspections are faster compared to conventional UT. So Zetec's TOPAZ product line delivers all the benefits of phased array UT: fast inspection speeds, full data storage, excellent imaging, multiple angle inspections, and flexible setups. TOPAZ 16 is a big value in a small size instrument. It's perfectly suited to handle thin weld and composite inspections. The TOPAZ 32 is the workhorse for high productivity in all industries, and with specific tools for stainless steel welds and time reversal inspection of composite material and complex geometries. And then there's the newest of the family is the TOPAZ 64, which combines the best-in-class code-compliant phased array UT and TOFT and industrial live TFM. So really there's a TOPAZ for every application for every customer. So this is an example of an application using phased array UT. This is a portable solution for a scarf repair inspection. The conformable wedge solution allows coupling when the surface condition is suboptimal. It's fully portable with the NDT paintbrush shown there on the right and TOPAZ, and affordable with a 1664 configuration. The inspection only requires a slight spray of couplant between the wedge and the inspected component, and the membrane is wear resistant and easy to replace. It's protected against air bubbles, which allow for multiple scanning angles, and it supports LM probes of all frequencies. The cross-section display allows for easy discrimination of the interface signal, scarf edge and depth, flaw, and the back wall signal. And then the C-scan display also allows discrimination of the base material, the scarf area and boundary, and flaw. So this is a second application for the phased array UT. This is a industrial solution for friction stir weld using the UT. It's optimized ultrasound phased array technique with a fast inspection. A single scan can cover the full weld using a quartz system and Ultravision 3. It's processed optimized with a software feature such as assisted analysis. Note that the unexpected flaw that was found in the test block, so it's circled there in red, that was not actually supposed to be in the test specimen and actually showed up when the phased array UT scanning was done. And that was confirmed with another technique. So moving to eddy current array testing, where Zetec has done an evolution in the aerospace NDT space. So a little bit of background on common NDT techniques for surface flaws. Liquid penetrant testing, known as PT, is also known as liquid penetrant inspection, LPI, or dye penetrant testing, DPI. Remains one of the most common NDT methods to identify surface breaking defects and discontinuities in material and other non-porous materials. So PT involves applying a colored liquid and allowing it to be drawn into minute surface openings by capillary action. Defects become visible under UV light or by contrasting color of the dye being used. Magnetic particle testing, MT, uses magnetic fields to locate surface and near surface discontinuities in ferromagnetic materials. So when there's very fine ferromagnetic particles that are applied to a metal, they'll be drawn into the discontinuities. And on the surface, then they indicate the presence of a flaw to this technician. So PT and MT are generally considered affordable and effective NDT techniques, but each does have its limitations. PT testing can only detect surface cracks and requires the purchase and handling of chemicals and disposal. And MT testing is effective only for inspections of ferromagnetic materials. So the inspection process of both techniques includes surface preparation and cleanup, can be time consuming, and the test results can vary depending on the skill and patience of the inspector, especially when the work environment is hazardous or uncomfortable or there's hard to reach inspection locations. Eddy current testing is capable of detecting surface and subsurface defects, including cracks, corrosion, and heat damage in conductive materials with a high degree of precision, while at the same time producing a digital record of the results. In aviation, eddy current testing is used to inspect skins, stringers, frames, rivet holes, tubing, and many other both ferrous and non-ferrous components. So eddy current array testing is multi-coil arrays that take eddy current technology many steps further. Array probes have multiple coils in the same probe assembly that are positioned at longitudinal, transverse, and off-axis orientations and are fired at coordinated times. With an array probe, users can capture more information in a single pass and dramatically increase the speed, accuracy, and the repeatability of non-destructive tests. So especially in large inspection areas. The inspection can change from a manual process that lasts several minutes to an automated one that takes seconds. So today the aerospace market is shifting toward multi-coil probes that can be used in a range of applications, which makes them feasible for anyone who wants faster and more accurate inspections. So scan speed, signal to noise ratio, and sample rate. ECA detectability is inversely proportional to the scan speed. So this can be an issue because the person is wanting to scan faster. Slowing down the sample rate will achieve better signal to noise ratio. So there is a minimum sample rate that's required to achieve the required data density. A high quality signal noise ratio eddy current instrument can increase the scan speed while maintaining the required probability of detection. So really a better quality instrument from a signal to noise ratio standpoint allows you to scan faster and keep that probability of detection requirement. And then both the, so for an ideal ECA solution, it consists of both the instrument and the probe. So those both play into the signal to noise ratio to meet the inspection needs. So next is going to be a demo of the signal to noise ratio versus sample rate, and this is using our new MIZ-21C and Surfex array probe.
This is a demonstration of how sample rate affects signal to noise ratio. Here we have the MIZ-21C array version with the Surfex array probe and a stainless steel calibration plate with EDM notches ranging from 100 to 10% depth. To demonstrate how the sample rate affects signal to noise ratio, this plate will be scanned using two different sample rates to compare the data. The MIZ-21C has an intuitive interface that is easy to use. The main menu has a list of supported applications. Within the application are the list of techniques for that application. Selecting the technique displays the parameters and their current setting. These parameters can be easily edited by selecting the Edit menu. We will set the sample rate to 150 samples per second for the first scan. Acquisition can be started by selecting the Acquire button. Let's perform a hardware balance, then scan the plate. To review the data, just select the Acquire button again. The data can be adjusted using the touchscreen interface. As you can see, all 6 EDM notches are easily visible. Let's take a screenshot of this. Now let's change the sample rate and see how that affects the data. Let's scan the plate again. As you can see, the noise level is much higher than before. The background noise is almost as high as the 10% flaw. With noise level as high as this, it is easy to see how a small flaw can be missed. With higher noise level, there is a greater chance of missing small flaws. Therefore, a high sample rate is not necessarily a good thing. What is more desirable is a high signal-to-noise ratio.
So what are some of the eddy current array inspection benefits? It's quick, it's clean and portable, and you can see there with the MIZ-21C, it's a handheld type eddy current instrument for array. It's accurate and performs high quality inspections. You can record the data. You can either record it onto the instrument or to an external USB device, which allows for expanded memory. You get greater coverage in a single pass. This is compared to like a pencil probe. And there's no need to store or handle chemicals. It's a clean inspection with little preparation that's needed to be done to the test material. And it's a low total cost of ownership. The probes typically are not consumable. So one application for eddy current array is friction stir weld inspections. X-ray inspections is time consuming and it can be difficult to get proper access for detectors. Liquid penetrant testing requires the handling of chemicals as well as time to prepare the surface and clean. And surface breaking cracks can be difficult for UT to detect. And in some cases, the size and grain structure of the friction stir weld can mask flaws for UT. And here it's shown there's 3 axial cracks, notches on the left, and then 3 angled cracks on the right. So A friction stir weld ECA solution would be using the MIZ-21C and the Surfix array probe shown there. Eddy current array is an ideal technique for use for friction stir welds. A small probe and instrument allows for fast and easy access to the friction stir weld. And then there's no preparation that you have to do for the surface. You don't have to use any type of handling of chemicals. So this is a scan image, which is actually from a Zetec MIZ-200 eddy current instrument using an ECA probe. And it's in a reflection driver pickup mode. The axial channel is set at 400 kilohertz. There's the 3 axial notches that I had mentioned. They're all detected in the axial channel. Notice that the superior signal to noise ratio quality with a very quiet noise plane and very prominent signals there, very easy to detect those signals. You can see that the noise plane has very little, it's very flat, so it's very clean noise. Also notice that the friction stir weld grain structure is not affecting the eddy current. So the flaws show up through the friction stir weld and it looks as though you're just scanning through a normal aluminum plate. You don't see the boundary of the friction stir weld to the standard aluminum. So that's a good thing because it means that the flaws show up, but the friction stir weld is not masking those flaws. So here you have 2 images. So on the left there's the axial channel and on the right is the transverse channel. So this is a example of dual frequency ECA inspection. The notches in the axial channel are not all detected. You can see on the right there that the right notch has a minimal signal and it's in the transverse direction. So the notches in the transverse channel are all detected since none of the flaws are in the axial direction. The right notch can be characterized then as a crack-like flaw because it's being shown up on the transverse channel but not on the axial channel. And this is a way to characterize the flaw type and orientation. So you can characterize it by seeing that a signal shows up on one channel and not the other when you're looking at axial and transverse. That indicates that it's a crack-like flaw. In contrast, if you have a signal showing up on both the axial and transverse, then that's indicating that it's more likely to be a volumetric flaw. You can adjust the scan angle to validate these results. And this is the process that's used. It's a very powerful process used to characterize flaws using ECA. So now we'll show a demo of a friction stir welding using eddy current array inspection with Zetec's new MIZ-21C array instrument and the Surfix array probe.
This is a demonstration of a surface array inspection on a friction stir weld plate. Here we have a MIZ-21C, a Surfix array probe, a calibration plate, and an aluminum plate with a friction stir weld containing EDM notches at various angles and the same flaws in the nominal section of the plate. The Surfix probe is designed based on a proven X-probe technology used in nuclear steam generator tubing inspections. This design allows for a high-resolution flaw detection with the ability to distinguish between axial and transverse cracks. The use of the encoder for sampling provides a uniform sample density independent of scan speed and gives the ability to measure the flaws, lengths, and location. The MIZ-21C's surface array application software is intuitive and easy to use. With the auto calibration feature, you can calibrate the data signal with just a few button clicks. Separate axial and transverse channels allows you to determine the orientation of the cracks. The merge channel combines the two together to provide a channel that can be monitored during scanning so that flaws will not be missed due to its orientation. Now let's scan the aluminum plate. As can be seen, axial flaws appear prominently in the axial channels, but are diminished in the transverse channels, and the same is true for the transverse flaws. The flaws that are angled appear in both channels, but are more prominent in one channel than the other, depending on its orientation. Now let's scan the other set of flaws in the nominal section of the plate. There is no difference in the data between the welded section and the nominal section of the plate. This is to demonstrate that the friction stir weld has no effect on the eddy current data.
So here is another application. It's a multi-layer bolt hole inspection. And one thing with multi-layer bolt holes is that it's not easy to determine which layer a flaw occurs. And this is particularly true when the flaw is very close to the transition between the layers. The eddy current method currently used is by putting some type of marker or tape on the probe to indicate depth, and then you have to sort of guess or estimate which layer that flaw is in, especially when it's close to the edge. In this diagram here, you see there's 3-layer Navy reference kit. One layer is 6.35 millimeters, the other is 3.18 millimeters, and then 7.92 millimeters. So the total thickness of all 3 layers is 17.5 millimeters. And then on the diagram on the right, it's showing the 3 flaws. You can see that flaw labeled number 6 is in layer 01, and that goes across the entire layer. And then there's 2 flaws labeled 5. Those are in layer 05 or plate 05, and they're smaller, like notch type flaws. And then in plate 03 there's no flaws. So a solution for multi-bolt hole scanning is to use a C-scan type method with the MIZ-21C, and this allows you to see the different layers. You get better probability of detection and characterization of the signals than standard impedance and sweep displays. The color 2D and 3D C-scan displays are which is coming from the eddy current array world, now being used on bolt hole inspections, and this is a real powerful leap forward in inspection capability offering. And then coming with the MIZ-21C is this superior signal-to-noise ratio to make the flaws easily identifiable. Shown there in the bottom is Zetec's new rotating scanner, ZM5. So the scan image is, in this slide here, is from a MIZ-21C eddy current instrument with a rotating scanner and a rotary probe that's used in a reflection driver pickup mode. The first channel is set to 300 kilohertz frequency, and the C-scan has a low pass and 2 high pass filters on it. So the first channel is used to detect the flaws, which you can clearly see both in the waterfall and the C-scan. So the orientation of the flaws in the bolt hole correlate to the vertical position of the flaw on the waterfall. So if you were to index it as the top of the waterfall is 0 degrees, then the bottom of the waterfall is 360 degrees in the bolt hole. So this is essentially taking the idea of the bolt hole and laying it out flat. And then from left to right is your scanning down the bolt hole, so it shows the depth of the hole. So this allows you to see the depth position and the angle orientation of where your flaws are showing up. So the second channel is set at 100 kilohertz frequency, and the C-scan has a high pass filter on it. The second channel is used to detect the layers. So here you can clearly see the on the waterfall, there's the blue sections or the different layers, and and also in the C-scan. So the 2 flaws that we had mentioned as labeled 5, which were the notches, you can see them clearly in the layer 05, and they're close to the edges, but you can see which layer that they're in. And then that center blue band has no flaws in it. That was layer 03, and clearly you can see that there's no flaws showing up in there. And then in layer 01 it has that crack that goes, or a notch that goes through the whole layer. So here you're seeing orientation of the flaws in the bolt hole and correlate to the vertical position of the flaw in the layer. So you see it both in the waterfall and the C-scan. So this essentially allows you to fully characterize the flaws in multi-layer bolt hole scanning, which is yielding you a higher probability of detection, and there's no guesswork in terms of which layer that flaw was occurring in. So multi-layer bolt hole inspection using C-scan advances the advancements from the eddy current array world being applied to bolt hole scanning improves the flaw detection capability compared to the traditional rotating scanner inspections that are being used today. Flaws can easily be assigned to a layer, and using an eddy current instrument with a high signal to noise ratio further improves the probability of detection. So now we will show a demo of a multi-layer bolt hole eddy current inspection using the MIZ-21C and a rotating scanner.
This is a demonstration of a bolt hole inspection using the MIZ-21C. Here we have the MIZ-21C instrument along with an Olympus Minimite scanner and probe and an aluminum bolt hole calibration block. The MIZ-21C comes with some great features for the bolt hole inspection, but the best feature is the C-scan display. Zetec has integrated a C-scan display for the bolt hole inspection, which can be used to identify the different layers and therefore allow you to know which layer a flaw is located, as well as increase the probability of detection. I will now demonstrate. As you can see, this instrument has the familiar XY display. But it also has the C-scan display, which allows you to see at what axis the flaw is located. Utilizing the dual frequency function, a separate channel can be configured to detect the different layers and therefore determine which layer the flaw is located. With the C-scan display, it is also very easy to identify and locate a flaw, thereby increasing the probability of detection.
So earlier this year, Zetec introduced the MIZ-21C. It's a truly affordable handheld eddy current instrument that's available in 3 models. The MIZ-21C is our dual frequency version that's a direct replacement for the MIZ-21B. And then there's a single frequency version. It's a lower priced instrument that is ideal for oil and gas applications and some aerospace applications. And then the MIZ-21C array, which offers our ECA capability and can be paired then with the new Surfex array probe. The MIZ-21C array really represents a breakthrough in value in being a handheld solution that offers eddy current array at a very attractive price, and really is operating in a space in its own. So what are some of the key benefits for the MIZ-21C? As you can see there in the image, it's lightweight and easy to hold. You can hold it with one hand. The instrument is competitively priced, especially for the array version. And then the superior probability of detection that comes along with high quality eddy current acquisition boards that's built into this instrument. It's compatible with standard probes and scanners that are existing and out there in the industry, and it's faster than doing a PT or an MT technique. No chemicals are required. The data is recordable. You can save the data files. You can exchange those between instruments. You can view them on a computer. And then the surface array solution dramatically reduces the inspection time. So the MIZ-21C is not exclusive to the aerospace industry. It's actually also ideal for oil and gas, transportation, power gen, manufacturing, and infrastructure. And below there you can see just a few of the different applications where you could take a MIZ-21C. Part of that is the eddy current array capability to do both non-ferrous materials, which are common in aerospace, but also ferrous materials that are common in a lot of the other industries. So this is a table of the 3 different models and what type of probes they support. So the 3 models, they all support handheld probes, plus point, cross point, weld scan probes, and conductivity probes. So that's with all 3 models. And the MIZ-21C and the array support the rotating scanner. And then if you want the array, you can move to the array version, which has all of the capability. You can also upgrade from any version to another version. So if you want to start with an entry model and move up to an array or something higher later, you can do that. You can also have a mixed fleet that you eventually decide you want to change the mixture and do upgrades of some of the other models. So the MIZ-21C, it supports a wide selection of Zetec probes. All of these are available now. There's pencil probes, blade probes, sliding, ring, spot probes, countersink, bolt hole, plus point and cross point, weld, surface array probe. And you can see there it's just one surface array probe shown, but we will be expanding into multiple other types of surface array probes. There are numerous adapters available to connect to existing probes that are out there, and we get requests to continue to add to different adapters, so we're adding to that every day. And Zetec also offers industry-approved calibration standards with various types of materials depending on your particular application. So here are some of the links for product info and training, and that has the ultrasound instrumentation we talked about, also the MIZ-21C and surface array probe. Interesting link is the MIZ-21C training link, where there's actually videos that supplement the user manual, and we have a kind of a philosophy to have a bunch of smaller videos that focus on features in the instrument that are easy to watch and find, that allow you to either train yourself, or if you need refreshment of previous training that you have, you can quickly focus in on a particular feature that you may need to get a refresh on. And these videos are getting added to continually, so this will be a spot where you can go to see a much larger variety of training videos. So that is the end of the presentation that I have.